Now let's crack straight on with currents and charges and get to Biot Savart's law, where steady currents, an electric current I is a flow of charge. If an amount of charge delta Q passes through an area perpendicular to the direction of flow within a time delta t, then the average current I is the delta Q over delta T, which is charge over time. Taking the quantities delta Q and delta T to be infinitesimal, we get the differential here, which is measured in amperes. Then the current density here is the current over that surface, where n hat is the unit normal, and this is a unit vector pointing along the wire perpendicular to the cross section. So the integral of I is I is the integral of the current density over a surface, the current through a surface. In a steady state, the total current through any closed surface must vanish. A positive or negative current would lead to a relentless accumulation of charge within the surface, which is not realistic. This is written as the current density equals 0. The integral of the current density over a surface must be 0. This is a generalization of Kirchhoff's node rule used in analysis of electric circuits. A divergence of J equals 0. Steady currents are divergence free. A current flows because electrons detach from atoms and are able to roam throughout. These are called conduction electrons. Assuming n conduction electrons in a volume V, then the number density n is n over V. The velocity of the electrons are tied to the temperature of the material. The collisions of these electrons with nuclei increase the temperature. Because the erratic motion, the average velocity of many conduction electrons is much lower than the thermal velocity of the average drift, and is called a drift velocity. Electrons moving along a wire each has charge negative Q. Diagrammatically here, V over a small increment of time, where the charge here is moving through that region from the point here, the chain charge has passed point P in time delta T, and as contained in the volume of V delta TA, where V is the drift speed and the volume contains NVA delta T conduction electrons. Therefore, the amount of charge delta Q crossing A is delta Q equals NQVA delta T. The average current I through the wire is at the differential charge with respect to time, which equals NQVA, where N is the drift velocity. The general expression for current density is given here. Now, unlike electrostatic point charges, current elements do not normally exist in isolation, but it is widely accepted that the force on a current element 1 due to a current element 2 is obtained like so. Consider two steady current elements, element 1, element 2, located at points R1 and R2, here and here. The two steady current elements 1 and 2 both in the plane of the page. The arrow delta F12 shows the force on the current element 1 due to the current element 2. The magnetic force delta F1 on the current element 1 due to current element 2 is given here, where mu naught over 4 pi is a positive constant. The unit vector r hat 1 2 points from the element 2 towards the element 1, and r12 is the distance between the elements. Now here we're writing them down explicitly. The magnetic force and a field due to a current element. Now the Biot Savart's law is a more general expression for the magnetic field at R generated by a current element at a point R sub 0, and it's defined as such diagrammatically here, which gives rise to the Biot Savart law here. And and a magnetic force on a current element is here. So that's that.